Hello student, I am Dr. S.L. Munde, Assistant Professor, Department of Mathematics, Sri RLT College of Science, Akola. Dear student, in previous lecture we have completed unit number 2. So in this lecture we will start unit number 3, and this unit number 3 is totally depends on a singularity. Okay. So we will see what do you mean by singularity and what are the types of the singularity. Okay. So we will see the some definitions related to singularity. So what is the first definition? The first definition is a singular point, or we can say that what is the singularity. Okay. We know the generally meaning of the singularity. So what is the mathematical definition of the singularity? Let f be a complex valued function defined on a region G. The point z equal to a is said to be a singular point or singularity of the function f. But when if f is not defined or the function f is not analytic at the point z equal to a. Okay. If the given function f of z is not analytic or which is not defined on a particular point, or we can say the particular point z equal to a, then we can say that that point is a singular point, or there is a singularity. Okay. So this is the basic definition of the singularity. Okay. That means singularity means the given function will becomes the given function will give the infinity term. Okay. So if you get the infinity, that means there will be a singular point, or that is a singularity of the given function. For example, if f of z equal to 1 upon z minus 2. Okay. So when this function will becomes infinity, if you put z equal to 2, if we put z equal to 2, so this will give 1 upon 0, and 1 upon 0 means that is a infinity term. Okay, and hence we can say that z equal to 2 is a singular point, or f of z has a singularity. Oh, okay. So z equal to 2 is a singular point, or we can say that singularity of f of z. Z equal to 2 is a singularity of the f of z. Okay. So this is the basic definition we have already seen in BSc third year. Okay. Now we will see what are the types of the singularity. There are mainly two types of the singularity. Okay. So what is the types of the singularity? First type is that is isolated singularity, and second type is non-isolated singularity. But this isolated singularity and non-isolated singularity also divided. So first we will see the isolated singularity. What is the isolated singularity? Let f be a complex valued function defined on a region G. The point z0 belongs to G is called isolated singularity of the function f. But when if z0 is a singular point of f and there exists neighborhood of z0, that means there exists r greater than 0, such that f is analytic in that neighborhood except that point, the point z0. If z0 is an isolated singularity, then there exists r greater than 0 such that the given function f is analytic in open circle whose center z0 radius r minus singleton z0. Okay. Then we can say that that point is a isolated singularity. Okay. So what is the meaning of this isolated singularity? Suppose that z0 is any point in region G. When we say that z0 is a isolated singularity, if f of z is a if f of z if z0 is a singular point of the function f of z, then there exists a neighborhood point, okay, such that f of z is analytic in that point, on that point, except the point if z0 is analytic f of z is analytic at that point z0, but there exist r greater than 0 such that f of z is analytic in a open circle whose center z0 radius r minus z0. Okay, so in this the given function is analytic, but not in this region. Okay, what is the example? Let f of z equal to 1 upon 1 minus z. This function is analytic for all the complex number except z equal to 1. Okay, so if z equal to 1, then this will give the singular point, singularity. But this function is analytic for all the complex number, but at z equal to 1, except z equal to 1. At z equal to 1, which gives the given function cannot be analytic. Moreover, there exists a neighborhood of z equal to 1 such that f is analytic in the whole neighborhood except at the point z equal to 1. Therefore, z equal to 1 is an isolated singularity of the function f. Then what is non-isolated singularity? The singularity z0 of the function f is said to be a non-isolated singularity if it is not a isolated singularity. For example, f of z equal to log z. This function has a singularity at z equal to 0. If you put z equal to 0, you will get log 0, and log z 0 means that is infinity. And z equal to any negative real numbers. Okay. So if you consider z0, then any neighborhood of z equal to 0 contains a part of negative real axis where log z is not a analytic. So therefore we can find neighborhood of the 0 of the point z where z is 0 such that f will be a analytic in that punctured disc. Punctured disc means at that point, 0 point. So therefore z equal to 0 is not a isolated singularity. So that is z equal to 0 is non-isolated singularity of the point of the f of z at a point z equal to 0. Okay. So what are the types of the isolated singularity? So there are three types of the isolated singularity. What is the first type? That is a removable singularity. Second is pole singularity, and third is essential singularity. So what is the first? That is removable singularity. Let f be a complex valued function defined on the region G. The point z equal to a is said to be a removable singularity of f if, but when first case z equal to a is an isolated singularity. Second, there exists a function g of z in an open circle center a radius r, such that g of z equal to f of z for all z belongs to open circle center a r radius r, singleton a. What is the example? Let us see the example. Let f of z equal to sin z upon z. So if you observe here, if you put z equal to 0, which gives the singularity, and which is the isolated singularity of the f. That is, f is analytic in open circle for the sum r greater than 0 except the point z equal to 0. Now let us define a function g of z on an open circle center radius whose center 0 radius is r. G of z equal to sin z upon z when z is not equal to 0. Second one, when z equal to 0. Since g dash of 0 equal to exist, if you take g of z at z equal to 0, then g dash of z is exist. So therefore g of z is analytic in an open circle center 0 radius are completely. Moreover, g of z equal to f of z for all z belongs to open circle singleton 0. Hence z0, hence z equal to 0 is a removable singularity of the function f. Second example, we can see f of z equal to 1 minus cos z upon z square, which is also a removable singularity. If you observe z equal to 0, which gives the singularity, and which singularity? That is isolated singularity of the function f. Clearly here we can say that f is analytic in an open circle whose center 0 radius r for the sum radius r greater than 0, except the point z equal to 0. So we will define the function that is g of z on a open circle center 0 radius r, and which is defined as g of z equal to 1 minus cos z upon z square, where z is not equal to 0. And if z equal to 0, you will get 1 upon 2. So here g of z is analytic in that circle, and therefore g of z equal to f of z. So hence z equal to 0 is the removable singularity of the function f. Next singularity, that is pole singularity. What is the pole singularity? Pole singularity is an isolated singularity z equal to a of the complex valued function f is said to be a pole if limit z tends to a absolute value of mod f of z equal to infinity. Then we can say that that is a pole singularity. For example, f of z equal to 1 upon z. So at z equal to 0, this will give the infinite terms. Is an isolated singularity of f of z, and limit z tends to 0 mod f of z, limit z tends to 0, you will get the infinity. So therefore we can say that z equal to 0, which is a pole of the f of z. Second example we can see, that is f of z equal to z upon z square minus 1. For at z equal to plus minus 1, so you will get the infinite term, that is are the poles of the f of z. So z equal to plus minus 1 are the poles of the function f of z. Third example we can see, for this can be written as z square minus I square. I square means that is minus 1, this minus that is plus 1. So this can be written as z square minus I square. So by using formula a minus b, a plus b, so you will get a minus I, a plus I. Okay. So here z equal to plus minus I are the poles of the function f of z. Okay. So this function is also at z equal to 2, z equal to 4, you will get the poles of the f of z. And third singularity is essential singularity. So what is the definition of the essential singularity? An isolated singularity z equal to a of a complex valued function f is said to be a essential singularity if it is neither a removable nor a pole. Okay. So essential singularity means it is not a removable, neither a pole. That singularity is called as the essential singularity. For example, f of z equal to e to the power 1 upon z. If you put z equal to 0, you will get. So here z equal to 0 is an isolated singularity of f of z. If you put z equal to 0, limit z tends to 0 mod f of z for a removable singularity, limit z tends to 0 e to the power 1 upon 0, that is, you will get infinity. E to the power infinity means that is infinite, does not exist. Okay. So therefore it is not a removable singularity. Okay. Second, consider limit z tends to a mod f of z, limit z tends to 0 mod e to the power 1 upon z. Okay. So for the simplification, we will put w equal to 1 upon z. Okay. So that is limit w tends to infinity e to the power w. So limit tends to w tends to infinity, that is e to the power a plus ib. Okay. So this can be written as w tends to infinity e to the power a e to the power ib. We can separate. So we know that e to the power ib by using Euler formula, this will give 1. So therefore putting limit, so you will get, if you put a to the power infinity, you will get infinity. Okay. So you will get a greater than 0 if a is negative, so you will get 0, e to the power minus a, that is 0, e to the power minus a, that is minus infinity, that is 0. So if a is a positive number, then you will get infinity. If a is a negative number, you will get 0. Okay. So limit z tends to 0, mod f of z does not exist again here. So therefore limit z tends to 0, f of z not equal to infinity, and also limit z tends to 0, e to the power 1 upon z is not equal to infinity. So therefore z equal to 0 is not a pole of the f of z, equation number 2. Now from equation number 1 and equation number 2, we can say that the given function at a point z equal to 0, which is not a neither a removable nor a pole. So therefore z equal to 0 is an essential singularity. Okay. So these are the types of the singularities. Okay. So in next lecture we will see the one theorem on this singularity.